Thank you so much. We are an aviation focused company, but we are working on things that I believe are truly relevant for all aspects and many industries where safety and machine learning are really or have to come together to provide meaningful applications. So today or for the next 20 to 25 minutes, there will be time for Q&A, I understand. I want to give you some insights into what it means for us to build machine learning or more commonly AI-based products for the aviation industry. And really the topic is all about safety here. So there are over 100 companies out there in what I find a really fascinating race to bring completely new types of aircraft to market. So I'm sure that many of you have seen at least some of these, from the volocopter to the Lilium. We work together with several of these, and we call these aircraft electrical vertical takeoff and landing aircraft, or eVTOLs for short. And they are, as I said, a really completely new type of aircraft that aim to make urban air mobility a reality. So the idea is that, if you arrive at JFK Airport in New York, that you can get your transfer to the city center for the same price as a taxi, but a lot faster, and avoiding all the traffic that these big mega cities have. So this is only possible if these companies become wildly successful and can operate at scale. For any of these to be able to operate at scale, they need to be able to fly without a human. And that's where we come in. So we are building a fully autonomous autopilot for these, one that doesn't require a human. So if we could move to the next slide, there's also a pretty big opportunity in existing aviation. So we see in these numbers that 3/4 of all non-commercial related accidents seem to be pilot related. So helping the pilot make better decisions, especially in difficult or even emergency situations, looks like a really good idea. And so what we see on the left-hand side here is what I would call a computer vision enhanced airplane. This is a schematic illustration, but on the next slide, if we can move there, this is what our system looks like in reality. So we focus on the visual aspects of flying first, which I guess is quite in line with this community. This is also called VFR flight. And some of the examples of tasks that we have to perform include localizing ourselves within the environment. So this is somewhat similar to GPS, just that we need something that's actually more reliable and also much more precise to allow precision landings, and also be able to operate in environments where GPS is not as reliable. And another task would be to detect other flying obstacles. So there is the corporate traffic, as we call it, that is other airplanes that send out signals that they are present. But we are in an era of drones and other flying things that we really have to see on a visual spectrum. So as you can see here, the system consists of a range of cameras around the airframe. We have one of our test drones in the top left, and then some general aviation airplane, the Cessna in the bottom right. And actually the eVTOL, one of the ones that I was just talking about, the volocopter on the bottom right, which has our 3-camera rig mounted to it for, that was during some early tests, I believe a year and a half ago, roughly. So it's really a range of cameras that we have around the airframe. And the system is designed in such a way that it can perform emergency tasks with a single camera only. So if everything fails, we said from the beginning we want to be able to perform the necessary tasks during an emergency with a single camera. But obviously for full functionality and also the redundancy that we need, we will probably look at a dozen cameras around the airframe. And you may ask yourself, why are we focusing on vision first? I mean, there are quite a few sensors and devices that could already help us achieve these tasks. The answer is that there are, in no order of priority, but there are certain advantages from a regulatory standpoint when introducing complex machine learning algorithms to aviation. And furthermore, we believe that vision is absolutely needed for full situational awareness. I mentioned that there are objects in the air, possible hazards that are non-cooperative, meaning we can only see them. We cannot spot them with existing machinery. And then, to be quite honest, you may as well, when starting a company, we are a startup. You may as well start with the hardest problem first. We know that, or we fully believe that this will be an integral part to the final fully autonomous solution, and we wanted to tackle this one first. So we've now seen what this looks like mounted to the aircraft. This is now what the aircraft sees. So this is our one of our use cases, landing guidance for fixed-wing airplanes. So this is a prototype I put together for the purposes of this presentation. What you see there is a system that only receives images from the environment, and it can sort of recognize the corners of the runway, and it tells us that it's actually looking at a runway. And then by using some properties of the camera and understanding where that runway is in the image, we can actually come up with an instrument that pilots are very used to navigate this plane safely down to the ground. If we move to the next slide, looking at these examples and at the problem at hand, it becomes very clear to us that it is pretty damn hard to get to autonomy without the use of machine learning, deep neural networks, or what people generally consider to be AI. And despite the accident rates for general aviation that I showed, and the part that human pilots play in this, commercial aviation still provides the safest mode of transport, and that is for good reasons. Everything that flies out there is tightly regulated and has to go through several layers of very rigorous certification. And when we introduce new AI technologies, we need to make sure that we can reach the same level of safety. So some prominent companies out there, they have company mottos that say move fast and break things. We really cannot do that. So we need to build our systems to the highest level of safety. And on the next slide, I have two logos here. More importantly, over the last 18 months, we sat together with EASA, which is the aviation regulatory organization over here in Europe, sort of the equivalent to the FAA, to think about how we can bring machine learning system to the required level of robustness for the industry. And in particular, we had to think about how to extend the existing regulatory framework to cover machine learning techniques, because this is something completely novel when it comes to certification. And as part of this, we created a first set of concrete guidelines that allows us to build machine learning systems and then also prove to regulators that they are safe. So on the next slide, you see the link to our report that we just published a couple of weeks ago. So the result of this work is roughly 130 pages of pretty dense technical content. And the way we went about this is that we really first thought about the risks that are associated with machine learning systems. So both what we know as machine learning scientists and engineers, but also taking into account concerns from other organizations and existing documents on this topic. And then we really went one by one to address each of these risks and concern that is out there. And as a result, every chapter is motivated with pretty fundamental theory. So we didn't want to introduce or start off our reasoning by looking at the latest and the greatest of machine learning from 2019. The field is evolving rapidly, as you probably all know. And so we wanted to make sure that this report is not sort of dependent on that speed, but rather makes use of the fundamentals. So we start off with theory that has really stood the test of time for 30 to 40 years. And then we looked into how we can adapt this theory to our use case and to modern deep learning as we know it. And then how we can practically implement that. So on the next slide, I'm not going to go into too much detail, but we realized that building machine learning for safety critical systems, and I guess for anyone that is not in aviation, this is just as relevant, really impacts all stages of a typical machine learning pipeline. So in aviation, we sort of differentiate between the design phase and the operational phase. So the design phase, everything we are doing in the office. And then the operational phase, as the name says it, when the system is in operation, in our case, flying out there in the world. And so we started by looking at how we can measure the performance of the system during the design phase, especially in the context of complex tasks and data. So how can we observe the performance of the system during operation? But then ultimately, we need to come up with guarantees that the system is safe during operation. And so the chicken and egg problem here is that we ultimately need to create guarantees for the system during operation. But in the light of the certification, we need to do that before we can actually put the system anywhere in, or near any operational use. So we have to sort of do that before. And the next slide actually summarizes what certification in aviation comes down to, a number that those that are in aviation have probably seen many times, in that for a critical system, such as a fully autonomous autopilot, we need to show that our system has a failure rate of less than 10 to the minus 9 per flight hour, or in other words, we need to show that the system cannot fail on average in 10 to the 9 flight hours. So at this point, I in a physical conference room, I often get the looks of people to say, "Oh my God, this is like close to impossible. How do you even do this?" And I kind of agree. I mean, it's ambitious, but actually, we can go a bit systematic about this, of how we can bring a neural network, a typical neural network based system to these required numbers. And this is especially interesting if we look at the next slide, when we go back to our use case from earlier, and we have, I would say, pretty good neural network running here that has that is processing these visual frames that are coming in, and it's on each frame it makes a decision, probably slightly simpler to what we see in the image here. It's just telling us, there is a runway or there's no runway, so it's sort of a binary decision problem. And if we assume that the per frame failure rate of the neural network is 10 to the minus 3, which is a pretty good performance, I would say, and it's running at 25 frames per second, meaning we're actually making a decision 25 times per second. We see that on the right, that our failure probability is actually approaching 1 pretty quickly, meaning we are almost guaranteed to make a mistake. I would say, I haven't figured out the exact number here, but I would say between 2.5 and 3 minutes. So the question is, how do we get from this to the 10 to the minus 9 that is required by the certification authorities, or more generally to any number that is required to make the system safe? And so starting with the next slide, if we can move on to that, I wanted to present a small part of that endeavor, but don't worry, I'll keep it at a relatively high level. For any questions, I think the report is a great source with further details, but you're also more than welcome to follow up afterwards. I only want to focus on a few tiny bits, which should give you an idea of the kind of work that is required. And in particular, we want to start by understanding how we can use certain characteristics of the data sets that we use during the design phase or in the office. So this is training data sets, validation data sets, and combine that with what we know about machine learning generalization to measure the model performance during the design phase, and then create performance guarantees of that for the operational phase. So in plain English, how can I measure how do I know that the performance I measure in the office will actually translate to any performance during operation? And the next slide has a very nice illustration that has a lot of detail behind it. But all I want to say here is that really, it turns out we can mathematically prove with a given confidence level, so up to some probability, that our model will actually have the same performance that we observe during the design phase in operation. So this sounds like good news, because if I can somehow make the model very good in the office, I can use these guarantees to pretty much prove that the model or also the system will perform equally well during operation. And this is important because all I can do is I can measure in the office during the design phase. That's something we shouldn't forget. And then in the end, what we are saying here is that with some probability, the performance is very close to what I know the model to do in the office. Now, to be able to create such guarantees, you need to dive a bit more into the data that you're using. And in particular, you need to look a bit more at the distribution of your data and how that is at the characteristics of the data sets that you're using. So on the next slide, I included a beautiful picture. But to be able to understand these distributions, we have to characterize our data sets, but more specifically also our input space. So the example that we have here, reminding ourselves of the system that I showed earlier as the visual landing guidance. This was a picture one of our test pilots took during a recent flight test. And the input space to our system is really just some language for everything it can see during operation. So it could, for example, be all the RGB images, so images that we take with any RGB camera that we could possibly ever record over Switzerland. So that is the input space to my model. And what we relatively quickly realized is that it's easy to talk about this, and probably everyone can envision what this space looks like. But it's very hard to explain this or describe this mathematically. And this is eventually what we have to do to be able to reason about the distribution of our data, what sort of images the model sees during operation, and then to create these performance guarantees that anything that we observe during the design phase in the office will actually translate to the real world when we put this thing into operation. So this is pretty complex and hard to describe on a mathematical level. But on the next slide, this is part of the approach is to use a technique that we often do, which is to reduce the complexity of what we are looking at. And in this particular case, we are reducing the dimensionality of the input space, so the space of all the images that we can see while we are flying over Switzerland. And it goes without saying, this doesn't only work for Switzerland. Can be applied in any sort of region. But instead of talking about all the images that I can possibly see and trying to somehow describe that, let's actually focus on a few aspects of flight and a few characteristics of the images that we take. You could imagine that we annotate all the images that we collect with a couple of attributes, I would say. So angle of approach, time of day, the speed that we had as we collected these images. And obviously there would be a lot more. But in this case, I chose 3 to be able to visualize this on the right-hand side. It gives us a nice 3-dimensional plot. This is actually some data set that I recently visualized and has a portion of our data. And then I can look at the distribution. Again, that's what I need to do. I need to somehow reason about the distribution. By the way, the goal I have is to show that the distribution of such a data set as I see it here is very similar to the distribution of data that I expect during operation. So I can look at this here and I can say, well, this looks like a relatively well-distributed data set, and I don't see massive gaps in that distribution. But if we look at the next slide, we say first that you can move on to the animation is not, thank you. The reasoning about this operating space that we just saw, this 3-dimensional plot, this 3-dimensional plot is actually not enough, because we in the end come up with an arbitrary characterization. I shouldn't say arbitrary, but it's human made characterization of this input space. and it will inevitably fail to describe some of the subtleties of our real input space, all the images that we can observe over Switzerland. So at that point, we had to pause for a second. We're like, we cannot really create any guarantees based off our own created and simplified operating space. So we need to go back to this real input space. And that operating space, the ones with the 3 dimensions or more that we created ourselves, is still very useful because it allows us to really reason about it and sort of look at all the different aspects that we've considered. But to come up with the performance guarantees, we need to still reason about this original input space. And we need to specifically show that the data sets that we've used during the design phase in the office, that they are independently sampled from the input space and also independent from each other. I think the latter one is even more intuitive than the first one. And so what we are proposing here is that for anyone that is really looking to use a machine learning model in any sort of situation where safety critical guarantees are needed, you should actually supply a second module, which also runs very low cost, runs during operation, and we call this an input distribution discriminator. And this input distribution discriminator is a generic concept, so it can be implemented in various ways, and all the details are in the report. But really what it does is it outputs a number in the end between 0 and 1. So you have your neural network running, and you have also this discriminator running side by side. And if this distribution discriminator tells you it gives you a low number, you actually know that the sequence of images that you're looking at is not independently sampled from the input space and not necessarily independent from each other. So meaning that your performance guarantees may not hold currently. And in essence, this means that whatever your network is saying right now does not make sense, or there's a risk that it doesn't make sense. The higher this number is, the closer it is to 1, and you define some threshold based off tests, then you know that actually your performance guarantees, they hold. Right. So this is all nice, and it's one of the big concerns that people have is, I've tested my model in the office. How do I know it will perform similarly during operation? But there's a second big concern around using models in real world applications. And on the next slide, I have a little illustration of some of the work that we have to do in addition to this, which is showing that the model is robust to variations in the input. So I've now shown, based on the metrics that I obtain on the data set that I have available, the model will perform, but I have no guarantee that the model will actually work in between my data points. So, if I approach a runway, we are still in the same use case, same context, that the model works at a 3-degree approach angle, which is a good approach. Then how do I know that the model will also still perform at a 3.2-degree angle? Or to use another example, I've tested my model in these lighting conditions with this brightness. If I make a slight change to it, how do I still know that it works? So we need to show that the model's output is robust to variations in the model's input. Very big topic. And so here we go back to what we call formal verification. So this tool that you're looking at here attempts to create lots of variations of the original image. So the original image is the big one that you see in the middle. And then we create a lot of variations of that in terms of brightness. We rotate it, we translate it. We can add lots of things to it. We can perform all things with it, so that we imitate different approach angles and so on. And we can use techniques to prove that within this space or within this cone that you see on the left-hand side, the model will always perform correctly. And if we find, it allows us to identify also offending data points, the ones that we cannot correctly classify, and we can eliminate them from we can eliminate that false behavior from the model to make sure that the next time it will actually do that. So with that, I hope I could give you a little, if we can move to the next slide, which is also the second to last one. I hope I was just able to give you a little glimpse of the sort of work that we are doing. And I think it goes without saying that making machine learning ready for safety critical applications or real world applications that require these high level of safety is a challenging and demanding task. Many people have told us it's impossible. We attempted to, or we still work on making this a reality. And I think it's very exciting, even beyond aviation. I'm obviously doing only a very small portion of the work myself. So we have roughly, actually, precisely, I think 47 people in the office after 3 years of operation. We include people from all sorts of different fields, software, robotics, and also pilots, so people that come from the aviation industry. And safety and sort of the regulatory aspects of what we are building has really been part of our journey from the beginning. And this EASA work is only a recent example. We are doing a lot more, and we have to do a lot more in the future. So, Jeff, if you could move to the very last slide. If you have any follow-up questions on this, please send me an email, or we have a couple of minutes left, I guess. I also heard that this is a pretty strong community. So not only thanks again for inviting me, but I was asked what we would like to get out of this community. And I think this is a shameless sort of advertisement that we are obviously hiring. So whenever you know good people, please send them our way. We're also fundraising right now. I'm probably not the right person to talk about this, but we are in full steam looking for more capital. And then I guess more sort of, fitting in with this setting here, we are always exploring good hardware. We have high requirements, strong requirements for the hardware that we are using. In particular, very good cameras. Right now, we have someone investigating the current state of the art of infrared cameras, IR cameras, and obviously, I would welcome any pointers there. But in the meantime, thanks so much for listening.